Greetings, class. It's great to be with you. We're going to do Whitlock and Schluter Chapter 16 on the correlation coefficient. Okay, correlation is the association or the relationship between two numeric variables. Keep in mind they need to be numeric. Correlation is a statistical technical term. You can't have a relationship between two categorical variables. We describe it as something different. Correlation coefficient is a number between -1 and 1 that describes both the strength and kind, or you could say direction, of linear relationship between two variables. The formula is expressed as the sum of the squares for x and y divided by the sum of the squares of x times the sum of the squares of y, and we'll put the square root here. That's the base formula. I will give some motivation for this in class. Now, as I said, there's two pieces of information that come from the correlation coefficient. The strength is determined by the absolute value of r, and r, as I said here, is the correlation coefficient. So just a note here for us. If we have the population between two variables, rho, the Greek letter rho is the parameter. Inside of our sample, r is the statistic. That's the sample correlation coefficient. So take the absolute value r, that gives you the strength, which is the amount or the quantity of relationship, or you could say correlation. Then the kind is the sign of r, okay? And that gives us the direction and the sign is either going to be positive or negative. That's it. The following diagram captures all of these observations. So a zero correlation is going to be nothing. Total random spread. Points are just spaced out. A 1 correlation means that we have points such that a line goes through them. Boom. Okay, that's a perfect linear correlation. Again, if you have a -1 taking the absolute value, still perfect negative linear correlation. The sign is changing, the strength is not. Anything in between is shades. I'm going to say -0.2 to 0.2 is no correlation because due to randomness, you can still get stuff in there. We'll look at this boundary in more detail later on. 0.2 to 0.6, rule of thumb, weak correlation. Again, this is just a rule of thumb. 0.6 to 0.8, moderate, and 0.8 to 1, strong. Okay. Correlation coefficient is not equal to the slope of the regression line. Carl Pearson enabled or found this connection between slope and regression line. I think it was Pearson. I'd like to talk about a picture of correlation. We said that the 0 is total random scatter, and as I look at this, if you basically put a circle around the points, not 100% of the points, but basically that's where they're falling, that's no correlation. Okay, here's another one. Notice the axis here is centered at 0, 0. Okay, so here's my circle. No correlation. This guy's a 0.5 correlation, which is in the weak range, and you see that we have a fat ellipse encasing these points. It's a positive weak correlation. Similarly, we're seeing it going on here. If I randomly sample from a population with a 0.9, which is a strong positive linear correlation, notice that the ellipse is now tighter. It's a thinner ellipse. These are just two random samples from which in the R scripts I show how this was generated. Okay, The book, I don't think, mentions this, but there's another statistic called the coefficient of determination, which is very, very useful. So we'll state it here. Correlation itself is not on a percentage interpretation. Coefficient of determination is. This is equivalent to what we had called R squared in the ANOVA. It's the proportion of variation in the response, that's the Y variable, that can be explained by the variation in X, the explanatory variable. Now, I will say in passing, correlation is symmetric, so you can switch your X and Y here and it works. In regression, you can't. The regression line will not be the same line if you switch your X and Y, but the association between the two variables remains the same. Now, we've talked about interpreting it. Let's look at an example here. Okay, if we consider Sir Francis Galton, he collected data on parents and children. He published the following diagram in 1930, and he flipped the axes, so his X is going to be here and his Y is here. These are the parents and these are the children's heights. He's taking the average between mom and dad, and then he's taking each adult child. If we were to draw it, we would go like this because we want our explanatory on the x-axis. So we're going to have a parent down here and then child. We would go something like this. At any rate, he collected this interesting data set and came up with a correlation coefficient of approximately 0.47. Okay, so what do we get from a 0.47? Discussing it up here, 0.47 is going to give us positive but weak correlation between parents and children. And that's where we get with our rule of thumb interpretation. Using the coefficient of determination, we take that 0.47, square it times 100, 22% of the variation in the children's heights can be explained by the variation in the parents' heights. That is, this variation right here, we've got about 1/5 of it explained by parent. About 4/5, 80% is not explained. We'll discuss that further in class as well. Okay, let's move into some specific calculations. Now here's the scenario. Deborah wanted to see if the amount of time spent studying for an exam really affected the grade. She asked 5 students in her stats class to record the length of time spent studying for the first exam. That's our explanatory variable. After the exam, she gets the scores. Okay. The data is shown below. I've got 5 data points here. So let's go ahead and take a look. To handle Deborah's data in R, I want to use our lecture notes file down at chapter 16. I've got direct entry for the data, makes it real easy. And we're just going to run the plot command to get ourselves a nice little scatter plot. Visibly, a tight ellipse would go around that, so it's looking strong. We'll cut to the chase, and COR is the command for getting the correlation coefficient. We get 0.945, so that's really strong. Let's go ahead and square it, and I'll get a 0.89. So looking in the lecture notes, the correlation coefficient is 0.95, strong positive linear association. We already said that. Coefficient of determination is going to be about 89% of the variation in the exam scores explained by the amount of time in study. Okay, let's show how to do this by hand. Now, I'm putting out the formulas here, SSX, SSY, and SSXY. The SSX we've seen before. So by way of review, sample standard deviation. If I write this, it hopefully rings a bell. We have x minus x bar all squared divided by n minus 1. Well, remember the shortcut formula. This top part right here is SSX, which we said was this formula right there. So that's by way of review. SSY is the same exact form, we're just switching x's and y's. SSXY is a little bit different. It's a relationship between both the x and the y jointly taken. So this is its definition, and here is its shortcut formula. So then, to get our r, we're going to recall that r is equal to SSXY over SSX, SSY under the square root. So we need those three components. Now then, here we go. Okay, SSX, I'm just going to look at the formula up top. It's the sum of the x squareds. So here's x, here's y. If I take x squared, 5.1 squared, boom, I'm right here. If I take 89 squared, boom, I'm right here. If I take product, 5.1 times 89, boom, I'm here. And so on down the rows. So then, the sum of x squared is 123.12 minus, I need the x I all squared, so that's going to be 24.2 squared over n, 1, 2, 3, 4, 5. That number turns out to be 5.88. Okay, sum of the squares for y, that's going to be 33,645 minus 407 squared over 5. That guy's 515.2. And sum of the squares xy will be 2022.4 minus 24.2 times 407, all divided by 5. That guy turns out to be 52.52. So plugging in now for my formula for r up in the right-hand corner is going to be 52.52 all over the 5.88 times the 515.2 under the square root. And in the arithmetic, we get 0.954. Okay. Now I've got a little section here on using r. This is just a direct calculation of the values that we just computed. And I'll tell you, you can rerun the identical scripts if you convert the name of any variable x and y that fit to x and y.